Welcome to the presentation about the investigation of porosity and carbonation depth in alkali activated GGBS mortar. My name is Tavasoli, the PhD student at the Technical University of Kaiserslautern and the researcher at the Institute of Construction Material Technology. In this study, I have used granulated blast furnace slag as a precursor which was activated by sodium hydroxide in order to provide the alkali activated paste. Additionally, I have used sodium silicate and potassium silicate as another types of activators as well as water glasses in order to find an optimized paste mixture to produce the mortar uh, in this study. Finally, I have exposed the produced mortars to the 3% carbon dioxide, and at the end, I have tested this compressive strength as well as carbonation depth and capillary porosity of the produced specimens. The materials which were used in this study are including sodium hydroxide, which was provided by our own in 16 molar solution, sodium silicate, which was industrially provided by having the molar ratio of 2.1, and potassium silicate, which was also industrially provided, having a molar ratio of 1.7. The GGBS, which was used in this study, had a plane of 4050 square centimeter per gram and a density of 2.5 gram per cubic centimeter. The activity of this GGBS was 1.02 at the age of 7 days, which was increased up to 1.25 at the age of 28 days. The standard sand, according to CN 196-1, was used to produce the mortars, and the mixture composition was according to EN 196-1, having water to binder ratio of 0.5. The mixtures which were provided could be observed in the following tables. I have considered 5 mixtures in this study. The first 3 mixtures are including the 3 types of activators separately in order to measure and evaluate the effect of each type of activators on the alkali activated slag. And thereafter, I have defined 2 optimized mixtures according to the results of previous mixtures. As I mentioned before, the mixture was provided according to EN 196-1 and the samples were provided in prismatic form. After the production of mortar specimens, I have cured them for 24 hours in 60 degree of centigrade in 92% humidity. Thereafter, I have put them in 20 degree of centigrade and 60% humidity. After 1 week, I have exposed the specimens to 3% carbon dioxide for about 7 days and then did the tests as mentioned before according to the standards as you can observe here. Let's go into the results of this study. Uh, Here I'm going to talk about the results of mercury intrusion porosimetry. In this table, I have brought the results of total pore volume of the first three mixtures, including sodium silicate, potassium silicate, and sodium hydroxide, in order to compare the effect of carbonation on the porosity of the matrices or medias which were activated by each type of activator separately. As you can observe, the carbonation had considerable positive effect on the mixtures in which the GGBS was activated by sodium silicate. We observe a huge reduction in the porosity during the carbonation. On the other hand, in the next two mixtures, mixture 2 and 3, no considerable changes in the total pore volume could be observed. In these graphs, we can observe the pore diameter distribution in the mixtures before and after carbonation. As you can see in the left diagram, uh, the non-carbonated specimen was tested, which was including GGBS activated by sodium silicate. And in the right diagram, we can observe the pore diameter distribution of the mortars uh, which were carbonated, and we can not see any considerable changes in the distribution of pore diameter. In this slide, I'm going to illustrate the pore diameter distribution of activated GGBS by potassium silicate. As you can observe, the pore diameter sizes increases considerably during the carbonation process, and also for the next mixture, which was in which the GGBS was activated by sodium hydroxide. We can easily observe a similar phenomena during the carbonation process, in which also the pore size distribution uh, was already changed, and the pore sizes were considerably increased. It means that the carbon dioxide penetration will be easier penetrate through the mortar media. In this slide, I'm going to show you the carbonation depth by using phenolphthalein indicator. As you can see, the highest affected specimens among these three mixtures was GGBS activated by sodium hydroxide, and the least affected specimens were those activated by potassium silicate. Although uh, during the carbonation, the porosity of the sodium silicate mixture I mean the activated mortar by sodium silicate was increased, but the carbonation reaction was higher than the specimens having 4% potassium silicate. Here I'm going to show you the diagram of carbonation depth. As we can observe easily that the silicate-based activators had the better resistance against carbonation, and also the potassium silicate had the best performance during the carbonation process, also increasing the dosage of activators will be helpful for increasing the resistivity of our mortar. In this slide, we can easily observe the comparison between the uh, GGBS activated mortars, which were cured for 7 days in room condition, and in the left columns we can see these diagrams, and in the right columns we can observe the compressive strengths of specimens which were exposed to 3% carbon dioxide for about 7 days. It could also easily observe that the compressive strength was uh, reduced by all the mixtures, and uh, the most effect could be assigned to the sodium hydroxide, and the by using the higher percentage of activators, the effect of compressive strength reduction will uh, be could be lower than the specimens having lower percentage of activators. Now I'm going coming to conclusion. The carbonation does not have any influence on the porosity of the alkali activated GGBS with sodium hydroxide and potassium silicate, but it increases the pore sizes, which will ease the CO2 penetration through the media. The porosity of alkali activated GGBS mortar using sodium silicate is highly affected by carbonation. However, no considerable change in the pore size distribution could be observed. Therefore, this type of activator could be proposed to be used in the specimens or mortars or concrete which are exposed to the harsh conditions and natural hazards, could we say. The rate of carbonation reaction in alkali activated GGBS with sodium hydroxide is considerably higher than those with the silicate based activators. It could be concluded that using potassium silicate as an activator provide the highest resistance to decarbonation in alkali activated GGBS mortar, and increasing the dosage of activator will also result in the higher reaction grade in precursor and subsequently improve the carbonation resistance. Here I'm coming to end, and thank you so much for your attention to my presentation.